Hello, everyone, and welcome to a new webinar from Optiwave. Today's webinar is Revolutionizing Photonics, and we will be talking about the new release of OptiSystem 22. And also, we are happy to be joined by Chiara Alessandra from Luceda, and she will be talking about big characterization in OptiSystem. And the webinar. Okay, let me see here. Okay, so in the webinar, we're gonna give some quick overview about Optiwave. Then we're gonna talk about the product line of Optiwave, then showcase the new components of OptiSystem, and then discuss the new improvements in this release. Then do some quick demonstration of the new examples added for these new components. And then I'll give the podium to Chiara to talk about Luceda and about the big design in IPKISS and how it's be integrated into OptiSystem. And then we'll demonstrate also an example on big characterization. Okay, so Optiwave is established in 1994, located in Ottawa, Canada, Ontario. And Optiwave developed software tools for designing, simulating, and for simulation and optimization of components, links, and systems, as well as networks. Optiwave offers these different packages of software, which offers a distinctive competitive advantage to shorten the product time introduction to the market through the simulations, which can be done ahead of prototyping, and then improve the product quality, because the simulation enables the users to investigate a lot of situations which cannot be basically built in the lab, and then also improve the enhance the productivity and cost effectiveness through the simulation. Optiwave products has been sold into different corporates and universities, governmental institutions, as well as research institutions in over than 80 countries. We sold over 1,000 licenses of the different software packages. The product line of Optiwave include system-level software, including OptiSystem and OptiSpice, which is an optoelectronic software. It's also being used for PIC designs. Then the component level software, which is including different packages like OptiBPM for designing waveguides, and OptiFiber for designing different types of fibers, OptiFDDT, which can be used for designing components, and OptiGratings, as well as OptiMode. And then OptiInstrument software, which enables users to communicate and control equipment remotely, and to set up characterization, and can be used for collecting data as well. If you are interested in downloading Optiwave software, you may go to Optiwave website and then go to the download page, which you will be able to download 30 days free trial of any software packages. First, you need to go to registration. You register your name and enter your password, and then create a password. And then you will be able to download any software packages. The software will be on C drive under program files Optiwave software. Like, as you can see here, the software packages can go there. And then if you select any one of these software packages, you're going to have the different directories for documentation, which is a very important resource. You have all the documentation, user manuals, and lots of information about the product release and so on. OptiSystem software has many components which enable users to be able to design the different subsystems and systems. It has over than 600 components, including light sources for CW lasers, LEDs, VCSELs, DFBs, white light sources, Fabry-Piro lasers. It has different types of modulators, Mach-Zehnder modulators, single drive, dual drives, and single port, as well as electro-absorption modulators, and so on. There is bit sequence generators, which is provide the users with pseudo-random bit sequences or user-defined sequences. You can load into these components measured bit sequences generated by, let's say, arbitrary web generators or ASIC devices. OptiSystem has components for OptiFibers, for single-mode application, multi-mode applications, as well as multi-core fiber applications, which can be single-mode or multi-mode. And these fibers or multi-core fibers can be designed using OptiMode software and then integrated into OptiSystem for characterization, for crosstalk, and so on. There is electrical modulators, there is quadrature modulators, there is orthogonal frequency division multiplexer components, which enable users to do subcarriers modulation. OptiSystem has support almost all the formats required in the industry for return to zero, dual binary, QAM, pulse amplitude modulation, probabilistic amplitude shaping, differential phase shift keying, and so on. There is optical filters, electrical filters, as well as FPG components, which use for filters or dispersion compensation or sensor applications. There is optoelectronics components, and you will be able to design ring resonators. Today, we're going to demonstrate in collaboration with Luceda the PIC design for demultiplexer and use these devices into as a multiplexer for demultiplexing for DWDM channels. And there is other components which can be implemented using OptiSpice software and integrated into OptiSystem as well. There is signal processing components, which includes DSP or equalizers, different types of equalizers. There is lots of components related to clock recovery, either 2R or 3R or 1R, depends on the application. There is algorithms for forward error correction, Reed-Solomon, or low density parity check. There is bit mappings. There is different type of bit mappings which can be used in the coding schemes. There is detectors. We have pen detectors, ABD. There is single photon detector component newly added. The old component in the earlier releases of OptiSystem, we called it SPD. Now we rename it and we call it photon number resolving detector, and we did some improvement and bug fixes on it. There is optical amplifier components. We support almost all doped material in fiber, where users can build their own amplifiers from scratch using these doped fibers, or there is amplifier blocks using these erbium components, or there is waveguide components. There is semiconductor optical amplifiers, Raman amplifiers as well. So lots of flexibility in the amplifier library. Users can do optimization for amplifiers or for any subsystem parameters using algorithms for optimization. There is single point optimization, multi-point optimization, Monte Carlo optimization, as well as gain flattening filter optimization for amplifiers. There is electrical amplifiers. We have transimpedance amplifiers, which supports linear and nonlinear regime of operations. There is automatic gain control amplifiers and limiting amplifiers. Passive components, whatever components you think of it in the field, there is a models and the component in OptiSystem which enables you to build your system. In terms of multi-mode support, we have multi-mode fibers, multi-mode amplifiers. So there is multi-mode erbium doped amplifier. There is a terbium doped multi-mode doped fiber, which you can build with it different types of amplifiers. There is visualizers, enables you to monitor the beam and so on. There is passive components as well supporting multi-mode. For channels, we have the fiber, we have the VCSELs, visible light communication channel, free space optic channel, underwater channel. And today we are going to talk about a new component we introduced called universal free space optic channel, and I'll discuss it later on. Visualizers, we have visualizers which mimicking the equipment in the field to measure optical or electrical, binary, memory signals. We have test equipments like light wave analyzers and BERT and so on. The components in OptiSystem, most of them, they have bidirectional operations. You can transmit signal from west to east or east to west. And then we support single and dual polarization as well. One good resource in OptiSystem software is the example library. We have over 1,000 examples in OptiSystem categorized in different categories, as you see here in these folders, and covers different applications, which includes advanced modulation. It includes radio front haul for 5G applications. We have lots of examples on optical amplifiers, microwave photonics, sensor applications from OTDRs, PHY OTDRs, different types of sensors, including photonic crystal fibers, which used for biosensing. You design these fibers in OptiMode, and then you can import it into OptiSystem. There is, as I mentioned, different types of wireless channel, and there is lots of examples on this in OptiSystem. Spatial division multiplexing, we support few modes, multi-mode fibers, and also we support the multi-core fibers, either single mode or multi-mode type of multi-core fibers. We have examples on quantum key distribution. We included in this release digital image processing, where we have 3 new components to address digitizing black and white images, gray images, colored images, and high and low resolution configurations. And then today, the demonstration with our collaborator from Luceda, Chiara, is going to talk about the PIC system characterization and do a demonstration on it. So as I mentioned, we have over 610 components in this release. We added up 9 new components, and we have over these 1,000 examples in OptiSystem. Now, one thing which is good about OptiSystem software is the co-simulation with other packages of Optiwave products like OptiGrating, BPM, OptiSpice, OptiFDDT, and OptiMod, as well as OptiInstrument. So you can use the other software to design some features or some components, and then you integrate them into OptiSystem. And also we allow in OptiSystem the user to write his own codes in MATLAB or Python or C++ or Scilab, and then use a component in OptiSystem to execute these codes to represent any devices which could be missing in OptiSystem, and then integrate it with OptiSystem. And today we're gonna talk about this new component. We call it OptiLuceda co-simulation, and Chiara is gonna talk about IPKISS software, which is used for designing the photonic integrated circuits. And now the good thing also about OptiSystem software, you can call it from Python or from MATLAB externally. So you can have your MATLAB code executed, and within it, there's some commands you call OptiSystem software. Or you can do it the other way around. You have a component in OptiSystem, and once you reach that component, you call MATLAB, let's say, and then execute it, generate the signal at the output, and then pass it into the other components in OptiSystem. So you can do the calling in both ways. Okay, in this part here, I'm going to talk about the newly added components, which is, there is 9 of them here. The first one is the universal FSO channel. This is a very comprehensive component right now addressing transmission of signals in air. And then we added up 3 new more components for image processing, where you digitize the image and then either black and white or colored or gray, and then transmit it over the channel. Then we had added up new components called second harmonic generator, which allows the user to split generate 2 photons. Let's say this is mainly for quantum application. You can apply a signal and then generate 2 quantum photons, or you can combine them to generate a signal at another double frequency component. And we created the new component SPD here, single photon detector, which generates a TTL pulses whenever a photon is detected. We're going to talk about this here. The old component, we used to call it SPD. We called it today in this release photon number resolving detector. We did some addition into it, as well as bug fixes. And then this component is basically is going to be used for counting the photons coming into the detector and giving some responses there. Then the new two components added hub for addressing the photonic integrated circuit characterization in OptiSystem is the Luceda and then OptiSpice component, which we will introduce in a later webinar and talk about it in more details. You can take a look at the new components and their location in the component library and some description on it using the released document of OptiSystem, which you can find it once you download the software under the C drive program files and OptiSystem. So this is the release note, which has all the information related to this release. And also one thing which you need maybe to consider is the data sheet of the new component. You can access them as usual from the help button here. So once you go to the component, double click on it, you get the component property window. Then you go to help here, and then you can access the data sheet of the component. Also, you can access the data sheet through the documentation in the component library PDF file, which you find it on the C drive, as well as on the Explorer as well. You can find it there. There's a version of it. Okay, in the release note, you might find also the improvement in this release, which includes, we did some improvements in the photonic power converter component, which is mainly used for converting high power light into electricity. And in this component, we added a new button, we call it run button, enable the user to make it easier to do the fitting for the two diode model used for this measured data. And also we allow the user to control the ideality factors N1 and N2 in the two diode model. We have added up a feature for the user to control the step size in the simulation of the optical fiber component. In the MATLAB components, it used to be all the values added to the components, either MATLAB or Python or C++, or even the main layout. It has a fraction. There is no integer value of the parameter. Now we allow the users to enter variables with integer values. Now, before, the users in MATLAB and Python, and especially in MATLAB, actually, they weren't able to access the parameters of the main layout, which is very important because you need to when you write your own code, you need to make sure that the number of samples and sample rates and bit rates, which is used in the code as well as in OptiSystem to be in sync. So you can read now these parameters from the main layout in OptiSystem and then manipulate them in the MATLAB code, basically. Another features we added up to the components which used to convert .dat file and to JSON or files or JSON files into .dat file using a run button and make it easier for the process. Now this JSON file conversion feature is important. We added up a new example to load data measured by equipment like Tektronix or Keysight or other vendors. And then you can pass it, let's say, to the DSP component, and the DSP component can be used to find the parameters for the adaptive filters and for other equalization components. We added up a new feature into the optical spectrum analyzer, single port or dual port, to allow the user to control the reference wavelength used to calculate the power, especially if you have the wavelength separated far from each other. So it's important to know the reference wavelength to use to calculate the power for the resolution bandwidth. And then as I mentioned to you, the improvement on the photon number resolving detector, we had allowed the user to load wavelength-dependent quantum efficiency. And then the PERT and the pseudorand bit sequence generator components, usually there is a leading and trailing zeros in the component. They were limited in their numbers. So we are at 1,000 before, so we are now allow it to be as 2 to the power 30 bits, leading zeros or trailing zeros, but you have to be conscious about the total number of available bits in the sequence, which is 2 to the power 31 minus 1. And then the BERT also, we allow the user to now, if you do sweeping of the signal iteration of the layout, then you can have multiple values of the bit error rate, let's say. So now we allow the user to have average bit error rate that results, as well as log bit error rate average values. Okay, so this is a new addition to OptiSystem features. You can find all of that in the documentation of the release note. Okay, so now it's gonna go into the examples added up for the components. I'm gonna talk about first the feature for this universal FSO channel. As you can see here in this pictograph, we allow the users to set the height of the transmitter telescope, the height of the receiver telescope. We can look into the evolution of the beam along the transmission. The user will be able to set up turbulence, and there is a built-in phase mask in OptiSystem as well. The user can load his own, let's say, measured turbulences phase mask. And then we allow the user to work with the Phi parameter or the CN square parameter. And then we provide the calculation of the CN horizontally as well as vertically. And then finally, we allow the user to work with different scintillation models. So originally we have log normal and gamma gamma. We did the modification on the gamma gamma, and we add up another feature in it. And then we allow the user to use new models like negative exponential K model and Malaga, where you can control the different aspects of the path of the transmitted signal here, as you can see in this plot. Now, one important also feature in this universal FSO component is the user before used to do the scintillation calculation for CN square, as well as the attenuation of the light propagated in the air externally using external component. We call them standalone components. In this new component, in universal FSO, the user will be able to calculate this parameter in the component. So there is a user-defined feature. You can set it up, and then you will be choosing the condition of the operation in the air here, for example, if it is rain or snow or whatever the condition, and if there is clouds, and then you can be able to find the attenuation at a specific wavelength and a specific height as well. Okay, so this is just quickly to show you the spatial phase mask, which you can load it. One of the examples we added up, it has this phase mask, and then you can calculate the basically the output of the system. Now, what I'm gonna go, I'm gonna move into the demonstration here. So I'm gonna go to virtual machine, where I'm gonna show you different examples. As you can see here, one of the examples, it's I did the calculation ahead of time because it takes some time to do some of these calculation. In this example here, what we show, there is data transmission over the channel in combination with high power laser. So there is a 10-watt laser and combined with data and transmitted over the free space optic channel. And then at the receiver end, you have the multiplex the data from the power, and then you can have the data analyzed and decoded, and then you can calculate the bit error rate. In this example here, there is we created different layouts for incorporating no temporal or spatial scintillation, and then this with temporal scintillation. So if you double click on the component, as you can see here, there is lots of options to choose from, and you can mimic the old FSO channel. So if you go into the component library here under free space optics channel, you have the FSO channel, the optical wireless channel, and then the line of sight channel. All of these components can be now kind of simulated in this component by the selection of these different parameters, and then the other parameters of telescope settings at the receiver side or transmitter side can be adjusted, can be open up or grayed, depends on the application. And then in this tab here, as you can see, this is where you can control the weather condition of the channel. And then in this tab, you have the scintillation models, and then you have these all new models added up into the component. And then in this tab, you control the spatial turbulence. Okay, so in this example, as I mentioned, there is different options with temporal scintillation, or with temporal and spatial, and with internal phase mask, or with external phase mask, which is user defined. And in the example, you can look at the data. For example, this is the eye generated of this PAM signal. So there is a different PAM signal with scintillation or without scintillation. In this example, you can see the eye, how it's clear, and you can see the effect on the level of the eye typically. So all of this information you can get about it. This part here about the photonic power converter, as I mentioned to you, in the component, we added up the user can control the ideality factor of the component. Here we have in this component 10 junctions. This is an example we did demonstrate it before using data collected from Broadcom as well as Characterize at University of Ottawa. So you can see this example here, the electrical current produced when you transmit 10-watt laser, and basically can be analyzed and so on. The other example here, in this example here, one of the examples in the OptiSystem, all the examples, we have 112 gigabit per second, dual polarization, 16 QAM transmission. We took the fiber channel, it used to be with fiber or other channels, and then we replaced it with a universal channel. And in this example, you can look at the after detection and the DSP and the decision component. You can look at the eye diagrams and so on. Another component which we talked about it is the second harmonic generator component here. The second harmonic generator component, in the component we assume phase matching condition, and you can set up the refractive index of the relative to the input beams or the output beam, and so on. So you can include some kind of losses, internal losses, and efficiency. And as you can see here, for example, if you in this example we have two light sources. As I mentioned, there is a phase matching condition assumed in this example, and then you can generate the second harmonic wavelength at the output of it. The other example in this one here, I'm going to talk about the image processing. And in the image processing example here, as you can see, we have in the tool directory, we have three components. One is black and white image digitizing, and then there is an image processing reconstruction, and also color image digitizing. So I'll talk about one at a time. But in this example here, we build, you have the black and white image component. You can load the image, so from your directory, and then you can either do set up the pixel size automatically or manually, or you can leave it, and the code or the component will be generating this pixel size of the image automatically. You can save the image file as a PNG image, and also you can save the data file if you are interested in it. So you can enable these features, and you can save the files. Now, in the other side, at the receiver side, you have the component which is image reconstructor. You need to enter the image pixel size in here, and then you can choose the option color image or black and white or gray image. And once you choose that, you can save also the reconstructed image if you select this field here, okay? Now, if you detect color images, you can choose high resolution or gray resolution from this button here. And in this calculation, once you calculate, you need to pay attention. You need to find the number of bits of the pixel, and then you match the number of bits with the number here, sample samples sequence length here. Sequence length in this example, 65,536 bits. If you multiply the number of pixels, your value could be a power of 2 or non-power of 2. So if it is power of 2, it's easy. It can enter right away here. If it is non-power of 2, what you need to do is select this field here, enable it, and then you can enter a non-power of 2 bits here, and then you can do the transmission. So one key issue here is just to make sure that the number of bits is equivalent more than the number of pixels multiplication of the size of the image. Okay, now after the calculation, you can take a look at the eye, and once the eye is loading, because it's a huge data file here, you can take a look at the eye and then analyze it and so on. Okay. Now the issue is going to be the size of this one. Okay, so let me open another version of OptiSystem until the image loads. Okay, it's going to take some time. What I need to show you here is the other components. As you can see here, the SPD component. So if you go to the example library here, file examples, and under component samples, then receiver library, and then here you can go to photo detectors and then SPD. In the SPD, as you can see in the photo detectors, we have the old examples, which is using the SPD, the old SPD component. We modify them and then we replace them with the not this one, this one's here. These old examples, we replace the SPD component and we put the new component, which is photon number resolving detector. Now, if you have the old examples, it should work as well, but you can replace the new components. Now, in the SPD component here, the new component we created, take one of these examples. Okay, okay, I'm not sure what's happened here. Let me just see. Okay, so let's take the example again. Okay, let me close. Okay. So this is the eye of anyway for the image. And then if I close this one, I can start again. So that's the example for the second, the SPD here, as you can see. Now, okay, I close the program. So let me launch it again. So this is virtual machine. Sometimes the communication with the license manager is, or the license is kind of sometimes having problems. But anyway, so this is the example. Now, if you do the calculation, okay, you can take a look at the SPD here component. What we did with it, we have two ports output. One is the electrical port, and the other one is the TTL pulses. These TTL pulses, you can, if you go to the component view in here, and let's expand it a bit, and then look at the 2D graphs. Under the graphs, you can have the generated TTL pulses. So this is the generated TTL pulses, which you can set up. It's a duty cycle. You can set up the rate of it. Now, this button here is going to tell you when is the photon comes. As you can see here in this component, we set up this sequence. We have 0, 1, 0, 1, 1, 0, 1, 1. And in this component, if you go back again, you have CW laser, you have attenuator. The attenuation is set to control the number of photons to be 1 photon almost per pulse. There is some randomness in here in this process, especially at the photodetector SPD. And if you look at the instances of the photodetector, if you look at the component view again, these instances, when the pulse comes in and there is a photon, there is an instance of detection of the photon. And with that, we generate a pulse, a TTP pulse, whenever there is an instance of photon. If there is 2 instances of the photon within the pulse, only 1 pulse is generated, as you can see in this scenario. one thing which you go in the component, you can set up different parameters of the component, the quantum efficiency or responsivity, but also you can set up the dimension of the photo detector. You can select the detection time. You can select the collection time, and all of that will affect the detection process, as you can see in the example here. So you can look at this kind of examples. This is a new component which very representative to what you can find in the field. Okay, so let me go back again into the presentation and try to finalize here. As you can see, the second harmonic generator, and this is the example of the photon detector. Okay, and now I'm ready to pass the podium to Chiara. And Chiara, please go ahead and then share the screen. I'm going to stop sharing here, and you can go ahead.
Okay, thank you. Let's see. Can you see my presentation now?
Yeah, perfect.
Okay. Thanks for the nice introduction. Super happy to be here presenting about this introduction. So what I'm going to talk about is a bit of an introduction to Luceda as a company, what we do, and how what we do, let's say, goes well together with what Ahmad showed you, the system level simulations, and how can you combine everything together. So for those of you who don't know us, Luceda is a company based in Belgium. We are now 10 years old, born out of the Belgian photonics ecosystem. We are really a photonic design company. So we are a team of photonics experts, and our customers are designers who sell software to design photonic integrated circuits. But we are also an ecosystem company. So we pride ourselves in having many ecosystem partners, among which we can find foundry partners, assembly testing, general ecosystem partners, and of course, software partners, among which Optiwave, with which we just started a new partnership. And what we aim to do as the Luceda is to provide a first-time right experience to photonic IC design. And we do that with our products, which are built in Python. So we are based on a code-driven flow, and we bring together all the aspects of PIC design in this one flow so that people can build chips that fit into products and products that work. This is an overview of our platform. Our core product is Luceda IPKISS. This is the platform that centralizes all the design aspects. So you have component and circuit layout, simulation, and ultimately, what you do, including validation and verification, it all leads to GDS export, and a GDS export that is correct according to foundry rules. We also have specialized tools that build on top of our core product, and we also have partner integrations such as the OptiSystem Luceda co-simulation that Ahmad has introduced. This new integration enables designers to fully simulate photonic integrated circuit-based products in a unified system. So you can leverage Luceda's layout and modeling capabilities of the PIC together with the system-level simulation features of Optiwave. Here you can see a schematic example of what's inside an optical transceiver design. So you would typically have a chip which contains the integrated photonics part, which you can design and simulate with our software. And then you can place it in a system-level environment where you can combine these with, let's say, the electronic drivers, DSP from Optiwave. So is a screenshot of the tool. Ahmad is going to show this more in detail later. But basically, you have this Luceda co-sim component where you can easily embed circuits that you have designed with Luceda. And it can work together with other components that Ahmad showed in his slides already to then run system-level simulations. So the question here is, how do you design the PIC, which is what you would use Luceda for? In Luceda, one flow is able to take into account the layout of the components, circuits, and simulation in one flow. You can do this parametrically, and you can do this according to the constraints imposed by the system and the foundry and the components that you're using. So in many cases, you will start from a schematic capture to, say, ideate on your circuit. Think about the high-level parameters you want to use for your circuit or system, and say think about the high-level specifications. And in a second instance, and you can do this in IPKISS Canvas, which is a schematic capture tool, which is part of the Luceda IPKISS. In a second instance, you will start by implementing the components and the circuit you need to let's say, design this circuit in layout. So the first step is component design, which you need unless you're using standard building blocks from Foundry PDKs. You can leverage the standard Python language that we use in Luceda IPKISS. You design components that are parametric in layout and simulation. You can usually fabricate them according to the, let's say, layer stack of the Foundry or the PDK that you're using, and run EME simulations or simulations with third-party tools, to which you can automatically export the layout you have created in IPKISS. So imagine you have, for example, a directional coupler, and we simulate it in FTTD. Then you can extract the S parameters, import them in IPKISS, and build a model for your components so that you are able to run, let's say, S matrix simulations, circuit simulations at any point in time without having to rerun FDTD every time. Now imagine you do this for a wide range of parameters. So in the case of the directional coupler, you could sweep the straight length of your directional coupler. So you have a parametric cell, you fix with the parametric layout, you fix that one parameter many times. Every time you run simulations, at the end, you can do a fitting of the simulation data with a specific fitting heuristic that is suitable for this component, and you obtain a parametric analytical model. What this means is that in your parametric cell, you can now change this length to the value that you want, and you have a parametric analytical model that will tell you how the component behaves for that specific parameter. And then you can use these smart components in circuits. So here we're implementing the schematic we saw earlier, which is a wavelength, the multiplexer. So you have, if you have two wavelengths in inputs, you can split them and the two outputs. And here, basically, what you can implement in a IPKISS cell that synthesizes this layout is a synthesis algorithm that basically takes the behavior you want your system to have and relates that to the design that you need to achieve. You need to achieve that specific behavior. So what does it actually mean? In the case of the multiplexer, you want to control the FSR, you want to control the center wavelength. So these will be the parameters of your cell, and in the back you have Python code, IPKISS code that do all the calculations of the physics to basically implement the right layout with the right length difference between two arms of an MZI, with the right straight length of the directional coupler to obtain this kind of transmission spectrum. And in the next step, you can then build more complex circuits. So here we are cascading MZI, basically the same multiplexer you saw earlier can be used as a cell that is then cascaded in a sort of tray. So if you have 8 input wavelengths in this circuit, they will be split among the 8 outputs. And this will be a type of, let's say, output simulation that you achieve by simulating such a circuit in IPKISS, where you keep a tight link between the layout and the simulation. So if the layout changes, you will see that in your simulation as well. And all these circuit design is backed up by Foundry PDKs, so you can design custom building blocks and use them together with Foundry building blocks. And very importantly, you also combine that with, let's say, requirements from assembly and testing in what we call assembly design kits or test design kits. And of course, the same flow that I showed you so far, so we saw that for the multiplexer, you can use it also for active components tailored for the application that you need to design for. Yeah, for instance, here you see an IQ modulator designed with your software for datacom applications, or an optical phased array for LiDAR applications. And you see these circuits being part of a packaging frame provided by Fix, which is automatically including your design through code. So you can follow this parametric framework where you can interchange and combine components you design with building blocks from PDKs. And then the behavior of these circuits is simulated according to the models built at component level. And then you send signals in, read signals out, and see how the circuit as a whole behaves as a, say, combination of all these subcomponents. And it is really where the integration comes in, because you can load these circuits inside OptiSystem and then manage your system simulation inside OptiSystem by deciding basically defining all your inputs and defining all your outputs, how you want to read your signal, what kind of information you want to get out of your system. You define the figure of merits that you want. And again, you can combine the Luceda component with all the other components from OptiSystem. As a final step, we have verification and tape-out preparation. So it's something you can do in IPKISS is, like in the end, what you're going to send to a foundry for fabrication is the GDS file of your layout that you have simulated and validated for simulation, but it also has to be correct in layout. So you want to check that the optical connectivity, it doesn't have mistakes and is implemented correctly, and that you don't have electrical shorts, that the waveguide lengths are implemented as intended. You can extract the netlist automatically to verify it, run post-layout simulations, also in OptiSystem, of course. Many of our customers also use 3D Export to verify the circuit or to just import the 3D model of a circuit in whichever tool they need to import it into, whether it's a simulator or a 3D visualization tool. And also very importantly, you have to prepare your designs for tape-out. So making sure that your design is accepted by the foundry, that you get rid of small, let's say, design issues that would not be accepted by the foundry. They would be raised by DRC. And they're talking about DRC. We're talking about design rule checking. So something that you can also do with Luceda is to create your layout using IPKISS and then run DRC using a single line of code. In this case, that's implemented with the link for Checkmate DRC, which is the recent tool developed by Spark Photonics. It allows you to run DRC checks on your layouts and then open them in K-layout. So circling back to conclude to the integration with Optiwave, the key benefits are that you can combine the layout and modeling capabilities of Luceda. So what I showed you now, I gave you an introduction to, together with Optiwave Systems simulation. And this doesn't require any manual translation, as Ahmad will show you in a bit. So you can embed photonic integrated circuits that made with IPKISS inside OptiSystem without having to manually redefine ports or manually extract the netlist. And this gives you like a complete electro-optical system digital twin. This can be done for many applications. So I showed you before a schematic of an optical transceiver, but it's just an example. Actually, we are very interested to see what you do with this. You could use this for quantum key distribution, LiDAR sensing, think about designing AWGs, radio waveguide gratings in Luceda, and then simulate them in OptiSystem. So there are no real limitations on applications, and we are curious to see what you're going to do with this. And I guess I'm going to stop sharing my screen now and get back to Ahmad.
Perfect. Thanks, Chiara. I think that's very, very good and very interesting for this kind of integration to allow users to characterize photonic integrated circuits designed by Luceda and into OptiSystem. So what I'm going to do here, it's show an example quickly about ring resonator, which is designed by IPKISS and then used for demultiplexing for DWDM channels. And it's characterized in a layout in OptiSystem. So the example, what we did here in the example, I'm going to show you in a minute in real life, but it's in the component here, which is the Luceda component here, co-simulation. we did first the characterization of the frequency response of the component. So what you can do, you can send an impulse here into the component and then characterize the output at every port of the component. And in the second part of the example, as you can see here, you can take a look at the response of the channels at the output port. And the other part of the example is we modulate different DWDM channels. As you can see, 4 of them here, multiplex them, and then transmit them through the big ring resonator demultiplexer, and then basically demultiplex each channel. And you can look at the output of any channels here and characterize the bit error rate, the Q factor, and how is it the device. Now, you can do a live different sweeps of parameters in the BIC design, and then every time you can take a look about the output results. So because OptiSystem allow you to sweep the parameters, you can do the sweeping and then look at the results. So let me go into the example here, which is going to another virtual machine here I have. And in this example, you can see we have pseudo-random user-defined, this component called user-defined bit sequence generator. We send only one bit here, 8 of them, and one of them is 1 and the other one is 0. And then you send it into these impulses. Now, in the main layout, you can set up the bit rate, you can set up the sequence length. Here we have 8. You can have the number of samples per bit, and then baud rate. This is for other application and so on. But once you set it up, you go to the Luceda component, and the Luceda component is very simple kind of structure for the component. You have you can select the domain. It is a frequency domain or time domain of the calculation. You can you can either specify the path for IPKISS locations, and or you can automatically detect that. In here, we can detect it automatically. Also, you can load the big file. So you can click on this icon here and then load the file from its location, as you can see here. And then once you load the file, what you can do the run button here. And this, once you do the run button, the component will be populated by the ports, input ports and output ports, depends on the design of the PIC. And then you can look at the PIC port information, as you can see here. So describing all this PIC information. If you enable this one, and you can take a look at all these ports and description of them. And then here, if you want to delete the file, you can click here, delete. So you can delete the file and then load another file if you wanted to do that. Once you do that, you can do the calculation. Once you do the calculation, I did the calculation ahead of time, and then you can take a look at results at every port of this demultiplexer. And this is the drop channel, as you can see here, the pass-through. And this is each drop channel. Now, the other layout, because OptiSystem allow you to have as many layout as you want, you can duplicate the layout as is, or you can create your empty layout. But in this layout here, this is the example where we use the system characterization of the PIC demultiplexer. We load again the PIC file, same scenario, and then create the ports. You have input ports and 5 output ports. And you can set up random bit sequence and lasers, the type of modulation you require to analyze this device with. You can get benefits from using the example library, which allows you to build on these systems. And then here at the device, as you can see, we have placed the spectrum analyzer, optical spectrum analyzer. As you can see, this is the new feature added about the calculation of the resolution bandwidth at specific wavelength. And you can also have the pen detector. If depends on the application, you can have pen or APD or SPD and so on. And you can have 3R regenerator, or you can build your own system by connecting the reference pulses and so on. So there is different options to have. And then this is the eye diagram where you can analyze the Q factor, the bit error rate, and so on. You can, any of these components, by the way, if you right click on the component, you can have component results. So you can have the available results in the component. You can have, as I showed you before, the component view, which you can take a look at some results here. If there is some plots, it will appear here. You can have 2D plots, you have 3D plots, you have reports. We have lots of lots of webinars which explains more details about the software. But as you can see here, with the integration of this component PIC device, you can analyze, you can do sweeping, you can do a lot of parameters to do a simulation ahead of building the device and investigate the device thoroughly. We will have another webinar actually on let me just get out here. We're going to have a more detailed webinar with Luceda, talk about the process thoroughly and in maybe a month or 2 months time frame. Okay, so this is kind of the results. Now, just to summarize here, we have this collaboration with Luceda to characterize photonic integrated circuits within a system. And you can look at IPKISS through the website of Luceda or this QR code. And also you can download OptiSystem software or other package of software through the website, and you can download 30 days free trials. I think with this, I conclude the webinar. Thank you very much for listening. And now we are open for questions, so we can answer some questions here. Okay, so let's start with the first question. We have question up from asking about, can the presenter show again about image processing? Okay, so let me go into the virtual machine again here and just show you the component. As I mentioned, let me open a new layout here and go to the tools library. And if you go to the components, we have 3 components here, as I mentioned to you. And the component in the color image, I talked about the black and white, but I didn't talk about the component. The component here for colored image digitizing. So what you do is typically you load, if you say here, for example, first of all, you need to select if in this component, if the image is gray. So if it's image gray, you select it gray, and then you load the image. So once you go to load the image, you go to the location of that image. Now, if it is not gray, it is colored, you need to choose if it is high resolution or low resolution image. So if it is colored image, there is 2 options. And the difference is the way we have the layers of the color coding is calculated. Okay, so the low resolution, the advantage of it is you have less number of bits produced for the digital image, and that would make the calculation faster. Typically, this is good option if you have, for example, eye diagram and you want to transmit the eye diagrams to do some analysis on them for machine learning or something else. But if it is you want to transmit high resolution, you can keep high resolution. In the component here, as the black and white component, you can either keep automatically detection the pixel size of the image, or you can enter it manually in this component. The most important part in the image reconstruction is you need to enter the pixel for the image. So the width and height, pixel sizes for the image, which you can, again, if you do that automatic detection of the image, it's going to be showing under the component here the size of the image and the width and the height. And then what you need to do is you need to enter them here and then choose the color of the color image, or gray or black and white. And then also you can save the reconstructed image in here into a certain location. So this is mostly about the image processing. Okay, so let me go back again here, take another question. Okay, so I think this question is, for which material platform and application can you design with Luceda? So maybe Chiara, if you could answer this question, please.
Yeah, of course. You can design for any material platform or application. We have process design kits so that you can use to design for foundries for like virtually any material using integrated photonics. And also for any application. So I showed a few applications on my slide, but there is no limitation on that. Of course, the most common application is Datacom, but we have customers working with many others as well.
Okay, thanks, Chiara. I have a question here again, and any latest update on optical code division multiple access, which relates to 2D wavelength and time? There is some publications actually done using OptiSystem on optical code division multiple access. So if you are interested, please send me an email. My email is here. You can send it to me, and then I'll pass you the information about it. There is a question here, maybe it says, maybe I missed it, but what is the content of IPKISS.py file that you load? Okay,
Hi, Ahmad. I can answer. This is Jem here. I can
sure.
answer that
Yeah,
actually.
okay. So Jem is the project manager for the OptiSpice and the coordination of the integration with Luceda. So go ahead, please, Jem.
So right now we're loading an IPKISS circuit. So it's something you can extract from mass layout or build it yourself in Python. So this is coming from CAPI IPKISS. Right now we're not loading parameters from the netlist onto OptiSystem, but so it's a fixed cell. However, it is a feature that we would like to add for the next release. So it's something we're definitely going to work on, where you can define your parameters in Python, and then you should be able to sweep them from OptiSystem to do a better analysis. So that's I think answers the question.
Okay, perfect. Thanks, Jem. Okay, let's look at another question here. How about the optical interface to the Luceda component? Is it possible to include the optical interface as well as using the laser source component, fiber component from OptiSystem library and couple it to the Luceda component to see how laser specs and optical coupling would affect the results? So the interface, as you can see here in the component, I'm not sure, maybe we can jointly, Chiara, answer the question here. So in the component, the PIC device inside the Python file, which Jem was talking about, you load it for in this component, it defines basically the ports, the type of ports it's optical or electrical ports you're getting out from this component, and then you can connect it, as you can see here, with any component in OptiSystem, and then you can, in the components, you can set up the component. It depends on the wavelength, depends on the component itself, because the library of OptiSystem is a huge in terms of flexibility to model. So this component is a CW model, which is analytical model. It's as you can see this is the model for the laser. However, you can have other type of lasers to investigate the PIC, let's say under different. If you go to transmitter library here, optical sources, you can have different type of lasers. You can set up the relative intensity noise of the laser. You can set up the side mode suppression. You can use VCSELs if you like. So it depends on the application you wanted to analyze the photonic integrated circuit. You can build the circuit around it in OptiSystem and then connect and analyze. And as I mentioned to you, you have a sweep feature. So you can do, for example, a sweeping, let's say, the power level here, and then you would be able to sweep as many times as you want, 100 times, let's say, and then go over the range of the parameter you need to look into it. You spread these values in different ways you wanted to do. There's lots of flexibility in the analysis. Chiara, good comment also on this.
Yeah, maybe to add on that, let's say when it comes to the PIC, the result of the simulation is as good as the models that you implement to describe the behavior of the components of the devices that are part of your circuit. So as I showed earlier, the circuit simulation boils down to putting together different components that you have simulated individually, and then you put together in a circuit, and then the circuit simulator basically calculates if you do a frequency domain simulation, it calculates the global S matrix of your circuit. So it really depends how complex or simple your circuits are, as long as your circuit models are. So as long as your models are capable of taking these parameters into account, then the answer is yes.
Okay, perfect. Thanks, Chiara.
Yeah.
Actually, we passed the hour here, and then what we can do here, we can conclude the webinar, and then we look at the questions and reply to these questions by email later on. Thank you very much for attending the webinar, and we appreciate your time, and looking forward to meet you in another webinar.